Hello and welcome to the second lecture of our course, and we would proceed with the state space realization. Just to have a recap, what we understood from the last lecture is that transfer functions are limited because of two major things. One is that they are defined for zero initial conditions, and the second is that they don't really give us a complete picture of what is happening in the system. They don't reveal the internal dynamics of the system, which is important to know in many cases, because if we don't know them, it might so happen that even though the output would be stable or would be regulated, there might be some internal variables which would go beyond the limits and would damage the system. So we need to have an information of those variables, and to in order to completely understand the behavior of the system, as we would give some control input to it. So we first so we discussed in the last lecture that there are three ways of deriving the state space realizations. One is from the physical systems, another is from the transfer function, another is from the block diagram. So in this lecture we would see how we can derive the state space realizations from physical systems and block diagrams. So this is a very simple or standard physical system that we all study, which is the mass spring damper, and this is a single mass spring damper system, and you can see that we can represent it by we know that we can represent it by this equation. This is simply a force balance equation. So the left hand side is the total force F in the direction of the displacement x, and the other forces Bx dot and Kx in the other direction. So this is the total external force, which would be equals to mass into acceleration as per Newton's law. So m into x double dot. So from this equation, so this is the differential equation of motion. This is the differential equation of motion. This is the starting equation. From here we can also derive the transfer function, and I have skipped some steps of moving variables from this side to that side. However, if we take the Laplace transform and do some algebraic manipulation, we would land up on this transfer function. You are when you are making notes, you try to make them as detailed as possible so that we can also give you maximum marks. So try not to skip the steps which I am skipping in the presentation slides. So what happens now? So we need to make the state space realization starting from this system description. So this is the system description of the system differential equation, or the governing equation of the system. So from here we notice what is the how we can go ahead with it. So normally what we do, we notice the highest order of derivative, and we take it to the we take it to the left hand side, and all the other terms we take to the right hand side. So the other terms which are present, so the other derivatives of the variables which are present in the right hand side, we generally assign them as the states. So we take x1 as x and x2 as x dot. So these are the two states we defined, and automatically by this definition you can see that x1 dot becomes x2. So after the definition of the states, what is our next task? Our next task is to obtain the first order differential equations of the states. So that is what we need to obtain. As if you remember, the state space realization is basically x1 dot equals to f1 of all the states and the outputs, so some function of all the states and outputs. Similarly, all the states would we need to derive, or we need to obtain all the first order ordinary differential equations governing the evolution of the states, these internal states that we are identifying, or the internal states that we are defining. So once this has been identified or defined, then we go ahead to understand we go ahead to derive the first order ordinary differential equations, which by which we would get an understanding of the velocity of each of these states. So if we have x1, we need to find what x1 dot is. If we have x2, we need to find what x2 dot is. In this way we have to go ahead. And from the definition of the states, we see that x1 dot is simply x2, and because x1 is x and x2 is x dot, so x1 dot is simply x2, and then x2 dot is x double dot, which is given by this equation. So from this equation we again copy this equation down in x2 dot. However, we take care to replace x and x dot with the states. So x is x1 and x dot is x2. So now we have a typical a set of first order differential equations which tell us the evolution of the states. And what is the output? We also need to write down the output equation. The output is simply this displacement x, so this becomes x1 in the state space representation parlance. So y is x1. So now we would not like to keep the state space state space representation in this form, which is an array of equations, but we would like to make this into a matrix. Because of obvious reasons, we would get a general solution or general understanding in terms of the matrices later on, and that also makes the representation more compact. So you can see the matrix representation is like this, and you can go back to the actual array of equations and go back and forth and understand that these two are the same. So I would not go into making you understand why these two are same. You can read the equations from the matrix as well, and make yourself certain that we are not doing anything wrong here while transforming the set of equations into matrix form. The next system that we would like to go through is the simple RLC circuit. So this is a series RLC circuit where a current I is flowing in the loop due to the excitation UT, and the output we are taking as the voltage across the capacitance C. So output is YT. So as you know from the Kirchhoff's voltage law, so the KVL equation is written in this line. So it is simply the drops across all these passive elements being equals to the excitation UT. So this is the equation, and in order to make a transfer function, we generally go to the next step where we differentiate it once more, and we obtain a relationship where we don't have integral terms. So we go to this equation, and where we are having all like so if we want to make a transfer function in terms of I and u, then we have to go to this equation. However, if the output is y, and you can replace this, so the output is yt equals to 1 by c integration I dt, because it is the voltage across this c. So you can replace the y here, and y dot, and so y dot will be this, and y double dot would be this. And if you want to get a relationship between y and u, you can use this equation itself just by replacing the I with y. So that is about the transfer function, but let us not bother about that so much here, because our main intention is to go to the state space realization. So to go to the state space realization, we have to choose, or we have to define two states, and which are independent of each other. So here what we do, so this is actually the skill we have to develop of how to define the states, so that our derivations don't become cumbersome. So this skill has to be developed by with practice, and by looking at solved examples. So I urge you to look into the books that has been referred, and as well as you will get some practice questions and tutorials to solve. So your practice will be carried on there. However, it is strongly advised to begin your practice before going into the tutorials, and for that you can look into the solved examples given in the standard books. So now what we do here we choose x2 as I, so not x1 as I, we choose x2 as I and x1 dot as x2. So when we choose x1 dot as x2, then x1 is basically integration of x2, which is integration of I. So this is x1 integration of I dt, so this becomes x1, and x2 is I, so this becomes x2, and this becomes x2 dot, the IDT becomes x2 dot. So now from this equation and this definition we are writing down the state space relation. So x1 dot is x2, that is already defined, so x1 dot is equals to x2, and x2 dot becoming I dot, so x2 dot is di dt, so we take di dt in one side and take all the other terms in the other side, and observe that I is x2 and integration of I dt is x1. So so what we get is x2 dot, x2 dot is di dt, so we also divide by 1 by L in the right hand side, so we get this expression. So you can do this derivation yourself and assure yourself that we are doing it correctly. So even by doing this, even by writing down these two while preparing the class notes, so you will get an understanding of how we are proceeding. So if you observe closely and if you pay attention. So here we are getting x2 dot equals to minus 1 by LC x1, because integration I dt is x1, and minus r by L x2 because I is x2, and another term we are also getting 1 by L into ut. What is y? Since y is 1 by c integration of I dt, and integration of I dt is basically x1, because x1 is integration of x2, x2 is I, so integration of I dt is x1, so this becomes 1 by c x1. So with this this now gives us the complete description of the system with the internal state dynamics being revealed and the output being related to the internal state dynamics in some way. Now we want to just represent it in a compact form, which is a matrix form, and this is the matrix representation. I have also provided the is by us and ys by us transfer functions in the left hand side, so you can go through that. So this is the state space representation, and you can verify it from the equations in the last slide that these are correct. These are correctly represented. So we represent it in the compact form. And now as you know that that the LTI systems, we are having the representation as x dot equals to ax plus bu, y equals to cx plus du. So in that parlance, this matrix becomes A, this matrix becomes B, this matrix becomes C, and the D is 0. So you could identify the ABC matrices in the mass spring damper system as well. So these are the matrices. Now just before going ahead for to the block diagram representations, I just want to make a comment that these definitions of states, or this choice of states that we have taken in the mass spring damper system as well as this RLC is not the only choice of the states available for us. You can very well define another state and use it in order to describe the system. You can try this. So maybe you can in place of x2, so you can define some other state. So maybe like x2 being defined as I here, so you could define it as maybe some voltage drop across, yeah, you can do this. You can define it as a voltage drop across this resistance R, and then you can try to derive the state space representation. It would also be another exercise for you. Similarly, in the mass spring damper, so this x has been taken as the output, and we have defined the states like this. So you might try to take another state x3, or you might try to take x2 as x dot plus x. So you try to take this x dot x2 as x dot plus x. I don't know how it will make your life how complicated it will make your life or make your derivations basically, but you can simply try to take this x2 as x dot plus x and see what happens. Some additional terms would come in the derivation, and that would also be that would also be relevant, relevant because x2 is not exactly x1. X2 has some other term, so it is not getting dependent entirely on x1, so it is still having an independent existence of its own. So you have to only keep in mind that for a second order systems you have to define two states, and you have to define them in such a way that the complete system description comes out. And when you define them in a bit different way than just this simple approach, then also you can come into a different derivation. So you can try that, out while you are practicing, and see what it comes out to be. However, what I want to stress here, that all such definitions of states are equally valid. The states are not very unique in nature, so the uniqueness is not there in the choice of states. So one can choose their states as per their wish, and this would be revealed in a general theoretical manner also while we go ahead in this lecture. However, you can try this out for these two particular examples by doing what I suggested. So this particular phenomenon is called the non-uniqueness of the state space realization, and will study about that later on. So now we go ahead to the block diagram, the state space representation from block diagram. So so the basic building blocks of any block diagram are the summer, the gain, and the integrator. So these are the basic building blocks, and these we use for LTI systems. However, if the system is a nonlinear one, we instead of the gain we can use a function block, and integrator is also often represented by 1 by s. So with this understanding, we go ahead and try to figure out what would be the block diagram representations of the systems that we just studied. And if we look back at the systems, if we see the general equation here, and this equation here, we will be able to understand that this block diagram of the series RLC circuit exactly maps to that equation, exactly maps to this equation, this one. So I will just go into the block diagram and tell you how it is doing. So here I have like intentionally avoided denoting what is x1 and what is x2. So however, as I already have mentioned in the last lecture, that the output of the integrators are the states. So you just need to understand which output is which integrator is outputting x1 and which integrator is outputting x2. Just look back at the equation and you will get to understand which one is which. So I guess this is x1. No, x1 is the output, I suppose. Yeah. So yeah, so x2. So this one would be x2 and this one would be x1. Yeah. So the u is passing through 1 by I think I missed one block here, which is 1 by c. So the output is basically 1 by c into x1, so there would be a block of 1 by c here. So while making your own notes, please correct this. So you see that x2 is passing through r by l, x1 is passing through 1 by lc, so this is getting added up and a minus sign is placed. Then u is passing through 1 by l, and that forms what? That forms what is here? X2. So this forms x2 dot. So then your equation is done, and here it is x2, which is x1 dot. So x1 is sitting here, here x1 dot is sitting, this is x2, so x2 is equal to x1 dot. Similarly, you can again look back into the slides and see what is the equation governing the mass spring damper system, and there also this is x1 and this is x2. So output of this last integrator is x1 and this first integrator is x2, and this block diagram gives the same equation that has been derived there in the state space realization. So since we could get this block diagram from the state space representation, similarly we can get the state space representation from this block diagram, and that is left for you as an exercise. So you simply assume the output of the integrators as x1 and x2 and try to do the exercise. So here also, here this 1 by c is missing, so please put that 1 by c block before y, and choose this outputs, choose the output of these integrators as x1 and x2. One thing maybe you can try this, you can say, so that would not make any difference. I was suggesting that to make this output as x1 and this output as x2, this would simply change the order of the equations. However, you may try to do that, and it will be a bit different. You can try to do that, and you can observe what is happening. So it will not basically make any sort of difference. Only the equations would be shifted up and down, and the output would be changed a bit. So that is all that will happen. So you can do that. You, for your own observation, I can tell it in my mind, but since you are new in this subject, so you can do that and observe whatever I am saying. So you can try this. Actually, you can try this. So take the second integrator's output as x2 and the first integrator's output as x1, and then see what is happening. You don't need to have any understanding of what exactly is x1 and x2 in terms of the physical system. So now when you are deriving the state space realization from the block diagram, you don't have any idea about the real physical system. You simply are seeing a block diagram. So x1 and x2 can be anything. This b, m, k, all these things can be anything. These are just some constant gains. So this doesn't have any meaning anymore. Okay, so when you have taken this out from the system, now they are simply numbers. So m may not mean mass, b may not mean the damping coefficient, k may not mean the spring constant. So they can be anything. So now it becomes a bit general. So from the actual system, when you take it out, this sort of a structure now reveals a general idea. So you can see both these systems, both the RLC and the mass spring damper, has revealed the same general idea. So this is the structure is same. So from structure wise, they are revealing the same idea. Okay, so this is the power of abstraction. So this is the power of abstraction. Though both the systems are very different in functioning, in their physical, in their actual physical quantities, one is dealing with electrical quantities, another is dealing with mechanical quantities. However, in the level of abstraction, both are same. So that is also something you can just sit back and observe and realize this. So this is the power of abstraction, and this is why we go for this sort of in the mathematical domain to understand real physical systems. So this is a very common question in the mind of UG people, why we are going in the mathematical domain when we have to really work with a very real physical system. So the idea behind it is this. So the mathematical domain gives us the power of abstraction. So in that abstraction we can analyze many different systems which are widely varied in their physical nature. However, they are similar in this abstraction level. So analyzing that abstraction leads us to an understanding of all those different physical systems. So that is what happens. That is the power of abstraction, and we are trying to utilize that. So here we see that both these systems having the same structure. However, we can have the block diagram in any different structure. So let us see this example. So this is some structure. Here also I have only limited myself to second order system. How you can say it is second order? There are two integrators. So two integrators mean the output of the integrators are the states. No other states are there. So because the dynamics is only created whenever an integrator is present. Dynamics meaning a first order differential equation. So only when an integrator is present, the input of the integration, the input of the integrator is, so if the output of the integrator is x, the input of the integrator is x dot. So the first order differential equation is created due to an integrator. So how many first order differential equations are getting created in this block diagram? 2, because there are two integrators. So output of one integrator you can write it as x1, another you can write it as x2. So I have chosen this as x1 and this as x2. The top one, output of the top one as x1, the output of the bottom one as x2. So if I choose this, so this example is now deriving a state space realization from a given block diagram. So any block diagram can be given to you, the process remains same. You have to simply look at it, observe it, and write down the equations. That's all. So you see here, what would be this? If this is x1, the output of the first integrator is x1, then this is x1 dot. So what is x1 dot? All these three signals coming in becomes equals to x1 dot. What are these three signals? See, a11 taken from x1. So x1 dot is a11 x1. What is the next signal? This is x2. So x2 coming through a12, a12 into x2. Another signal u coming through b1 plus b1u. Done. So you can so in the first step you can write down the equations separately, and then in the next step you can make this matrix write it in matrix form. For your own practice, first write down the equations separately. So x1 dot you have written down, x2 dot is this, which is the output of this summer. So what is coming in the input of the summer? So let us consider it later. So this signal, what is this signal? Again another summer is there. So this signal is summation of this and this. So this signal is basically, this is x1 is coming through a21. So there is no like dot here, that means it is jumped. So a21 is coming here. Then what is this? A22 into x2. So a21 x1 plus a22 x2. So this signal gets completed, plus b2u plus b2u. So we have to check the this these summers are having some plus minus or what. So here everything is plus, so there is no minus sign in these expressions. What is why is the output? It is taken from these two signals, c1 into x1, c2 into x2. So this is coming from here, c2 into x2. That adds up to form y equals to c1 into x1, c2 into x2. Your job is done. So given any block diagram, I am sure that you will be able to make a transfer function. So you can practice this I'm not sure if you will get such examples, so much of block diagram to state space representation examples, but you can create any such block diagrams and do it for your own practice. Of course, you will be uh, given some block diagrams for your practice as well as for tutorial submission, so you can do them then there also. So with this, I come to the end of this lecture. I hope you got to understand what I wanted to convey, and you can go back and look into it again and again. So this is a new topic, and the representations is new, so you have to make a bit of an effort to pay attention and also keep on practicing side by side in order to really get an understanding and some level of expertise in this subject. So thank you. Thanks for your attention.